So let's start with definition of definite integral. So we have definition of definite integral. So let's say we say a function y equals to f of x defined on the interval a to b is integrable if the following limit exists. So when n goes to infinity, if we take the sum from 1 to n of all the value exists, and there's a slight difference between the notations that I used in the classroom and here, which is I used xi in the classroom, which is just one endpoint of the subinterval of a and b. But here I denoted as xi star, meaning that this xi can be any value inside this subinterval, i's subinterval. And what is this delta xi? So delta xi is simply the length of subinterval. So I'm going to use this as b minus a over n. So here xi is just the ith point. So we have a plus I and b minus a here. So really delta xi is not about a formula in terms of I, but we use in notation I just to make us just to coincide with the general definition, which I'm not going to go deeper than this. So anyway, what we have defined here is the integrability of a function over an interval. So once that is integrable, then we say this limit, whatever that is just denoted as this symbol. Okay, so this whole thing, the SAB fx dx, is one thing that represents this limit. Okay. So what is this does? What does this do? So we have we all know that this is area under the graph of a function, and what really is actually defining a geometric invariant called the area. So if it's not any region which is not a rectangular region has to be we need to use integral. We need to use the concept of definite integral in order to define what the area is. So only possible way we can define an area is just approximation. So we're gonna take a subdivision of this interval. So here we take equal subdivision here, and then so when I take xi star at every subinterval, I'm taking a random point. Let's say this is my ith interval. Then I just pick a random point in between this subinterval, and then I take the value of function, and then I take the height of that point to be the height of the rectangular box, a rectangular region, and then I take the area of a rectangular region, and then I do that for every subinterval. So of course, if I do that to approximate the entire area, I have some error. But since I'm taking a limit goes to infinity, if it is always the same limit, no matter how I choose my xi star, it's going to be what is called the area, right? So that's the definition of integral of single variable function. And here is the comparison with the integrability of two variable function. So a two variable function on, again, it's a rectangular region, AB, is integrable if this limit sum fxi star yj star delta xi delta yj, where I from 1 to n, j from 1 to n exists for any xi star inside of xi minus I xi and ji star inside of yj minus 1 yj, and the rest of the part is similar. So xi delta xi is just denote the length of subinterval, and delta yj is the length of subinterval in y-axis. And here I also assume that xi is just the equidistant subinterval. So a plus I and b minus a, yj is c plus I d minus c. So in that case, we say then we define the double integral over the rectangular domain of two-variable function to be this limit. Okay, so just abbreviate this part. So again, this whole thing is just one notation indicating the value of limit. And we also talked about the meaning of this. So we are actually looking at the volume under the graph of function f. So here, let's see. We have interval from a to b for x-axis, intervals to c to d on y-axis, and above xy plane we have z-axis, and the surface here is the graph of the function z equals to f of x, y. And we're doing the same thing here. So we are subdividing this rectangular region into smaller subregion or subrectangle. And let's say I take one of these subrectangle. So it's the ith subinterval from the x-axis and j subinterval in terms of y-axis. And then I take a random point. So here, I can take any xi star and yj star whenever it's in the subinterval. It means that this xi star or yj star lies within this subrectangle, and I take the height at that point. So this is the point on the graph of this function, and this height will serve as the height of a thin cube lying above this small rectangular region. So here, let's use the blue one here. So this kind of rectangular box has volume now, and we do this for every subrectangle. So, and then add all the volumes of thin cubes to get the approximates of the volume under the graph of the two-variable function f. So if this exists, no matter how I choose my point for each subrectangle, then I can define the volume under the graph as somehow kind of invariant number, right? So we can define the concept of geometric invariant called volume using this definite integral. So this definite integral is now called a double integral. So this is just normally called the definite integral. This is called the double integral. And this is double integral. Okay. So we now also talked about how do we generalize, or how do we use this definition in order to define the double integral over non-rectangular domain, and how to compute the double integral using iterated integrals. So I'm going to review that part again. So let me erase this. So here, definition. So if D lies inside of big rectangular region, and this function f of xy defined on D is integrable if the following holds. So if the function f, let's see, large f, so different from the small f given in the definition, which is defined on the big rectangle by the following way. So we have large f of xy has a value same as small f of xy if x and y lies in D and it is 0 otherwise. So otherwise means that xy still lies in the big rectangle, but xy does not lies on D. Okay, if this function is integrable on the rectangular region. Okay, so let me read the definition again because it might confuse some of us. So we are talking about the integrability of a function, small f, of two variables x and y over the domain D, which lies in a big rectangular box or rectangular region. But that integrability is dependent on the integrability of another function called large f of two variables x and y, which is defined now on the rectangular region, whose values is either f or 0. It's f whenever we have xy lies in the domain D, 0 otherwise. So if I draw the picture, so let's say D is right here, and we have A, B, C, D here. So this large f has no value, 0 value outside D, but still it is defined over this rectangular box, which means that, which is different than function small f, because small f is only defined inside of this domain D. So again, the function is defined by the rule of assignment and the domain. So this function f and the large f has different domain. But since this large f is now defined on the rectangular box, we can use the definition of definite integral, which assumes that the function is defined over the rectangular domain. And this integrability of this large f is telling the integrability of this small f. Okay? So ideally, it's the same thing as what we have done. We are trying to get the area under the graph of a function over the domain D. So let me draw a picture here. So let's say we have same figure D over xy plane, and we have graph of function which just lies above this here. So z equals to fxy here. So I just want the area or volume under this part of the domain D, but we can't just find it right away unless we have a rectangular domain. So we kind of artificially make a rectangular domain to surround the entire D, and then look at this kind of shape where it has some kind of a cylinder sticking out from this plane xy, and then outside of this cylinder we have all 0 values outside here. So when we take the integration of this function, and we're kind of assuming that our function, the red part is the graph of this large f. So red part is the graph of large xy here. And if we take the area under the graph of this large f function, then it is same as the graph of function, the volume under the graph of small f over the domain D, right? So that's one way we can extend our notion of definite double integration. And we also talked about the Fubini theorem. So let D to be the collection of all the points defined by the following inequalities. So we have x lies in between A and B. And according to x, we also have y, lower bound, and upper bound. So then if I draw the graph of this domain, it looks like somehow A to B, and here is our lower bound, and here is our upper bound. So this is y equals to g1x, and this is y equals to g2x. We are looking at the area in between these two graphs, which doesn't intersect each other, right? And we want to take integration over d. So what is our question is, oh, by the way, so if this is integrable, then we define integrable, and then we define the definite integral f x y dx dy to be same as a b c d large f x y dx dy. Okay, so this notation is defined to be this, right? And this is defined by our limit, definition of limit. So whenever I say this, you have to think about this situation, right? So it's a double integration, but Fubini's theorem, so it's not definition here, so it's Fubini's theorem. So it says that if f of x and f of y are continuous on the domain D, then this can be computed by iterated integral g1, g2, f x y dy dx. Okay. So again, let me emphasize, this left-hand side and right-hand side are totally different concept. So left-hand side is a definite integral, which indicates the area, volume under the graph. And on the right-hand side, we're kind of doing a partial integration. So we are doing a subsequent integration by single variable. So here we have first integration by y, assuming x is kind of constant. Just like when you take the partial derivative, we take other variable as if it's constant. So we take x to be just as if it's constant, taking the derivative of y, so we get rid of y. And then the whole thing, the whole expression, let's say this is ax, is a function of x. So then we can take the derivative integration in terms of x again for the function ax, right? Whatever that is. So what is the meaning of this? So again, let me draw a picture. So every time I try to give you the meaning, I'm drawing the picture, and I also want you to think of this way whenever you try to memorize the concept. So let's say this is the case, a to b, and we have two boundary, y equals to g1x and y equals to g2x here. And here is our boundary here. And above this domain D, we have a graph of a function, right? So we kind of have a graph of a line above here. So the red part right here is trying to get the integration of f of xy by fixing the point x. So we're fixing a point right here, So I'm looking at the section of D, but not really just the D, because I'm taking an integration of f. So I'm taking the domain to be just the section line that crosses the D at the point x, but what I'm really looking at is the area sitting above this line, right? So this area, which is the sectional area at the point x, is a of x. This is a of x. This a of x, right? And then what I'm doing here in the next integration is I'm integrating this area over this perpendicular direction. So you can think of this way. So ax is the sectional area, and when I take integration of a of x dx, it's kind of approximated by, without using the limit, it's approximated by sum of a of xi times delta xi, right? Or if you want to, you can use xi star if you want to. But then, what is this? So this is the volume of thin slit, right? So slit between these two sections right next to each other, very thin, because its width is just delta xi, but still it's a volume, right? And you add all the volumes, then you get the entire volume, approximation of entire volume. It is approximation because when you take the volume of thin slit, you're kind of assuming it's a cylinder. So even though the actual volume has changing the one part of the boundary by its shape of a graph, but when we take this amount, we're kind of assuming that the area, the bottom area, is fixed and you have a fixed height. So it's approximation. But what happens when you take the limit? What happens when you want to make it an equality here? So then the approximation becomes exact number. So basically, this is the volume under the graph of z xy on D, right? So which coincides with the meaning of our original derivative, our original double integration, right? So you can convince yourself by using this argument why this inequality holds. And there's another version of this Fubini theorem, and which is, you can also, so there's a version 2, so not version 2 is separated with this part, is instead of having minimum and maximum range of y, you can set your minimum and maximum range for x by fixing y. So instead of having this, we can have this. So here y is changing from c to d, and here the minimum x is governed by h1y, and here the maximum is h2y. So for every y, you have a fixed range of x from h1 to h2. Then what happens? So in this case, if you want to take, so this is d, if you want to take the double derivative of the function defined on d, if the same condition holds, if this condition is true, then this is same as cd h1x h1y, h2y, fxy, dx, dy. Okay. So these two cases are in some sense, it's a very simple case because you only have one set of bounding functions to define the entire domain. But in most cases, you have to split your domain in order to use one of these Fubini theorems. So I'll give you an example, just a conceptual example here. Okay, so let's say we have this kind of domain in xy plane. So this is your D. So I have a function defined on D, and I want to find the double derivative of this function. So there are two ways of finding this integral. So one is you can find the big rectangle lying, which contains properly the entire D, right? So if you can find such rectangular domain, then this is the integration. By definition, it's same as the integration over this rectangular domain of large fxy, where this large xy is either f or 0 if xy is in D, otherwise 0 otherwise. Okay, but this may not give you the exact answer. It may not give you the way to solve the double integration by hand. You might use this. You have to use this method if you want to use the computer to approximate the value, or approximation is the only way. But if you want to get the hand calculation done or the exact value, then you have to go for the Fubini theorem. So now I cannot fit this D into any of these shape, right? So because if I want to take this entire D and try to find G1 and G2, there's no single G1 and G2. For example, here, this is minimum if I take this part, but still this is minimum here if I take this part. So there are, some complication here. So you have to choose which direction you want to go. Let me use this one. Let's say I fix X and then find the bound of Y. So then I have to cut this domain into vertical lines like this. So I'm gonna, let's say, I don't need this part. So I'm gonna take this D1, this one thing is big D1 and this D2 and D3. So we have 3 regions. And if I want to take the derivative the double integration over D, it's just the area under the graph of a function over D. So I can get the volume separately, 3 different volume, which doesn't intersect each other, and then combine all together to find the total volume. So this is same as D1 f dx dy plus D2 f dx dy, right? So look at the D1 here. So D1 is bounded by this line above. So let's call this y equals to G21x. And then also it's bounded below by this curve here, right here. So this is yg, let's see, 11x, okay? So it's not 11 and 21, it's 11 and 21. Okay, so this integration over D1 is computed by Fubini theorem. We are assuming that the function is very nice so that our partial derivatives are all continuous over the domain D. So it can be written as the following. So let me put A and here A1 here and A2 here. Okay. So when I look at the D1, the x range only from A to A2, right? So A to A2. And then where does y range? So it's from G11 to G21, right? F dy dx. Okay, so I can get this part. I forgot the D3 part. So how about D2? So D2, look at these 2 lines. So it's bounded above by this curve. Let's call this y equals to 2x, and bounded below by this curve. So this is y equals to G12x here. So the double derivative over D2 is from, now in this case, A1 to A2, because all the points in D2 has x coordinate in between these 2 numbers. A1 to A2 and G12x and G22x f dy dx. Now let's get to the third part, so D3. So here D3 is equals to, so we have x range from A2 to B, right? So A2 to B. And how about the upper and lower bound? So here, there must be, actually it's not B, sorry. So it's, let's say A3 here. So we put the vertical line which touches the rightmost point of this domain D. So instead of B, so B may kind of, so here again, so it also is not actually A. You can have A0 here because A may not just touching the leftmost point of the domain D. So instead of A, let's put A0 here. So just put the vertical line which tangentially intersects the leftmost point of the domain. And same for the rightmost point. So it's A2 to A3. And look at these 2 boundary lines. So here one boundary, and here we have another lower bound. So let's call this as G23 and this as G13x. Okay, so then we have G23x and G13x, and then the same f dx, dy dx. So if you have a complicated domain, then you have to split it up in order to make it into the case for the Fubini theorem. You can do opposite way, so you can go for the opposite direction. So in that case, you take a horizontal line whenever it tangentially touches the domain. So I draw this way, so it's easier to make tangential vertical lines instead of horizontal lines. But if the situation is given out otherwise, you can do either ways. Okay, so that's for the double integration, and I want to make also the review for the triple integration. So here is the definition first. So a function, so now it's three-variable function. Still, it's a real-valued function on a box A, B, C, D, A, F is integrable if the limit n goes to infinity, I from 1 to n, j from 1 to n, and k from 1 to n of f xi star, yj star, zk star, delta xi, delta yj, delta zk exists. So there must be something more coming from here, but I'm going to omit this because I'm assuming you already understood what's going on. So we have xi, yj, jk, xi star, yj star, zk star, all lies in ith, jth, and kth subinterval of x, y, z axis. And delta xi, delta yj, delta zk are the lengths of subinterval of x, y, z axis. And if this limit exists, no matter how we choose xi star, yj star, and zk star, we call it integrable. And this limit, the whole limit, is called the triple integral of the function over this rectangular cube, and denoted by three s's, dx, dy, dz. Okay, and it's called a triple integral. So what's the meaning of triple integral? Well, as I said, it's going to be the volume of four-dimensional object, but that's not intuitively clear. So the most intuitive way of describing the quantity of this is the mass. So let's say we have a cube, which has same as this one, and we call, so there's a point inside of a cube, let's call it x, y, z, and let's say f x, y, z is the point density at that point. Now, density is always measured by volume of the kilogram or mass unit per volume, right? But here, point density means that it has no unit of volume. So we're kind of assuming that the point itself has a density somehow. So if I multiply this point density value with the length unit, then it means the density of the unit of length, and then per unit of length. And if I multiply the point density value with the area unit, then it's the density per area unit. And then if I multiply with the volume unit, or the value of volume, then it's the density per volume unit. So we have density right here and the volume. So it's density, point density, and this is volume. So it kind of gives you how much mass does it has within this volume. So in a small rectangular box, which is at the ith, jth, and kth of this subinterval on x, y, z axis, has this much mass. And we are adding all of them. And when we add them, we kind of approximate the entire mass. But when you take the n, the number of subintervals goes to infinity, then we get the smaller and smaller error. And if this limit always exists to the same value, then we can define what we call it as a mass of the entire volume. So this thing is the mass of this cube AB, CD, and EF. So again, using this definition, I can define the triple integral over any type of shape, three-dimensional shape. So this is defined to be the integration over the cube of bigger function, kind of bigger, but the values are not the bigger. So fxyz is either f or 0. If it's f, only when xyz lies inside the volume, and 0 otherwise. So we're kind of assuming that this volume lies properly inside of this cube. Okay, so we know that this is defined by the above definition. So whenever you want to try to define the integration, triple integration over random shape, then just we go for the bigger box and then do it. And we can approximate properly. We can actually compute the value using the Python code or computer program. However, sometimes we want to find by hand, or we want to find the exact values, and you have to go for the Fubini theorem. So there are also many versions of this Fubini theorem. I'm going to show you the two versions of this Fubini theorem for triple integral. So first of all, so omitting all the necessary conditions, the triple integral over this cube of the function is defined to be iterated integral, 3 iterated integral, like this. So here, our bound is always constant, so because we have a rectangular box. So we can switch around this integration order, but you have to be careful that this dz, dy, dx indicates the order of the integration. So you have to keep the order. I mean, you have to change the order, or you have to change the bounds of this integration accordingly. Okay. So in other words, I can still I can write this as EF AB F, but then it means that this AB is the range for x. So I'm taking integration of x first, and then EF is the range for z. So and then I'm taking integration by z, and then CD is the integration by y. Okay, so I can switch around, but just make sure that you don't mix these bounds of the other variables. And this is one simple case. There are more complicated case. So for example, let's say our volume is defined the following. It's not rectangular, and we can somehow find the entire range of x, but for each x, I also have the range of y according to x, and I have a range of z according to the value that I fixed at the previous stage. So we have, if I have fixed x and y, then z can only move in between h1 and h2. So what happened in this case? How do I use the iterated integral to find the triple integral? So the Fubini theorem says the integration over v of the function is same as this iterated integral, g1x, g2x, h1xy, h2xy, f dz, dy, dx. Okay, so let's think about the meaning again. What are we doing? So we are taking a mass of the volume V, assuming that F is the point density. So we need to check whether the right-hand side gives the same meaning. So let's say this is our volume here, and let's say this is my domain D when I project it onto xy plane. So assuming that this axis is somewhere here, okay, and even though we are taking an integration over the z first, we have to think about the meaning from the outside. So we first fix our x. So we fix our x. When I fix my x, I'm looking at the section of D. In other words, I'm kind of looking at the section of this volume when I just cut through this line x here, right? And then when I fix y, I'm kind of fixing one point on this section. But this one point is actually a collapse of all the points lying above in the section of V, right? So when I fix x and y, I'm looking at the line that is on the section of this volume V. And this is the domain, or this is the kind of interval that I'm taking my integration with f, right? So this is the length. I'm taking the small part of length, which represented by dz here. So I'm multiplying the density function or density, point density, with the length unit. So when I do the when I take the integration, this gives the mass of the line segment right above this point, right? And then I take the integration by y. So I'm taking the masses of this line segment and I'm moving y across this section to find the mass of the section. So mass of this area section, right? And then I'm moving my x from the lowest part to the highest part. So then I'm taking the masses of section across this entire volume, so I get the mass of entire volume. So it's the mass of the volume V. So we get the same meaning of this triple integral. And in the class, we kind of mentioned that if you have given the triple integral, there are more than one way to find the expression using the Fubini theorem that computes the same value using this iterated integral. And when you try to get the correct bound, you have to think about the geometric picture of the volume V to do that. Okay, so that's kind of review, and what I want to talk about today is not too much. I just want to talk about the project topic here. So here, let's see. Our project 7 is about Cauchy-Crofton formula. So what is Cauchy-Crofton formula? So think about the curve. It could be a closed curve, which means that starting and ending point are the same, like this one. Or it could be just open curve, whatever. It can have different starting and end points. Whenever you have a curve, you want to find the length of a curve, right? So how do you get length? Well, first of all, so what is the length? So let's say this is curve. Definition, the length of C. What is it? So there are, the conclusion, if I spoil the conclusion, the length is also a geometric object, just like the area or volume. It's an invariant geometric concept that can be defined on a geometric object, and it is also defined by the definite integral. So in order to see that, let's think about how do we possibly measure the length of a curve. So first of all, if you think about the moving point along this curve, let's say this is my point, P here, and it's moving around this curve in a certain time, then there must be a speed of movement of the point, right? So let's say the time equals to 0 whenever the point is just about to start, just starting to move. And then let's say the time t equals to large T when it stopped moving, either finishing the curve or went back to the original starting point. So then the length of a curve is just integration of your speed, right? So the total length, total distance you traveled is the integration of your speed. So if the speed of point P at the time t is vt, so I'm not saying that this is velocity, it's a speed, then it's always positive. Then if you take the integration, you always get a positive number, which is the length of a curve, right? So how do we get this? How do we get the speed? Oh, there are other ways of getting the speed. So you can find the position of your point by parametric function. Let's say ct gives you the coordinate x and y according to t. And if you take the derivative of your position function, then you get the velocity function, right? So c prime, so this movement, c prime is the velocity, and this is x prime t, y prime t. So velocity is not a speed. Velocity is not a speed. If you get the norm, the size of the vector, that's the speed. So v t is c prime t, but if you want to get the speed, then you have to get the size of this vector, which is square root of x prime square, y prime square, right? So you can get this by integrating, once you know the parametric function, the square root of x prime t square, y prime t square, right? So that's one way you can define the length, because that's the only way, intuitive way of finding or computing the length of the curve. And what else? What other way you can define the length? So there is one way you can also define the length by approximating, which is, let's say, using this figure here. Suppose that I have a point P, and I'm still moving my point, but instead of thinking about the time, I'm going to subdivide my curve into smaller pieces. And then if I enlarge this one piece, let's say this is kind of exaggerated here. So let's say this is P0 and P1, and here we have Pi minus 1 and Pi. So my curve is curved. It's not straight line, but I can make a straight line between the endpoint and the starting point. And the length of this line segment is almost equal to the length of a curve segment in here. So instead of finding the exact length of the curve, I can approximate my length to be the sum of the length of the line segment joining these points, consecutive points. So this is defined to be the sum of all the line segment p minus 1 to pi, right? So this is the length of line segment joining pi minus 1 and pi. So how do you find the length of a line segment? Well, if you know the coordinates, let's say this is xi, yi, and this is xi minus 1, yi minus 1, then this is same as square root xi minus 1 square and yi minus 1 square. So if you take, so there's no time variable involved, but if you kind of modify this formula a little bit, let's say this xi, yi is obtained at the time ti, and let's say we have t0 to tn, which gives you the time when it's arrived at pi points. Then I have ti minus 1 square divide and ti minus 1 square divide, and inside of this big square root here. And since I have multiplied this, I can take ti minus 1 multiplied outside. What do you see here? So outside we have delta t, which is becoming dt in our definition of the definite integral. And on the inside, we have the square of the ratio between the displacement of x coordinates and then the change of time. So this is basically the derivative of x, the rate of change of x position, which is x prime. And here it's y prime. So it's getting exactly x prime and y prime when I take the limit, because this is just average rate of change of x and y. But when n goes to infinity, the interval becomes small, and this also becomes small. It's going to be the limit of the ratio, which is the instantaneous rate of change, which is x prime and y prime. So therefore, these two definitions are the same. Now, what are we going to do to talk about the Cauchy-Crofton formula? So since we now have the definition of concept of the curve, length of a curve, we can make sense of what the Cauchy-Crofton formula says. So it says once you have a curve C, which is bounded, then the length of a curve, so this is the length of curve C, equals to 1 over 2 integration over n rho theta d rho d theta here. So what's the integration domain? So rho can be 0 to infinity, and theta is from 0 to 2 pi. And what is rho and theta? And what is n rho theta? So here we have curve, and we have line. So this line can be parameterized by rho and theta. I'm going to tell you what the rho theta is later. And this n is the number of intersection between this line, parameterized by rho and theta, with the given curve. So n rho theta is the number of intersection between L rho theta and the curve C. So here, if this is the entire curve, even if I take more parts of this line, it's not going to meet anywhere else than this. So this line has n equals to 1. So we just have n here. Okay, so this function is just it's not a continuous function at all, right? So it's always value of positive or a 0 integer. And what is rho and theta? So rho theta is a parameter that determines the line in the two-dimensional plane. So let's say this is my x and this is my y, and let's see, we have the line here, and we're kind of assuming there is a direction of the line. Then we take first the distance between the origin to the closest point in the line. So we get the low rho here. So this is the displacement of the line from the origin. And we have the angle theta here. So this measures how much your line is tilted from the direction of the x, positive x here. So then you can get all the possible position of the line. So for example, if you get the opposite direction here, so if you have a line here, you're kind of assuming that this line is going in this direction, and then you kind of get the theta to be this theta here, okay? Yeah, so this is theta and rho. So what is this? So going back to our formula, it says that on the right-hand side, it seems like it's nothing to do with the length. We just count the number of intersections. And it says if you just have a counting function, and if you take the integration, this double integration, then you get magically the length of the curve. It's a very strange thing going on, right? So I'm going to give you one example why this must be true. And by the way, don't be alarmed when I say the domain is from 0 to infinity, because the curve is not going diverging to infinity. If the curve is diverging to infinity, we don't even have to compute the length because it's automatically infinity. So we always have a finite curve. So if it's a finite curve, then we don't get the rho go to infinity, because if the curve is somewhere here, even no matter how big it is, if you have an origin here, you can always take a big ball that contains the entire curve, and the radius r is going to the maximum bound of the rho in our integration. So we don't really need to take the infinity as the bound. So I just put the infinity just to make sure that it applies to any kind of curve. But when it gets to real computation, you don't need infinity. You just find big enough r that contains the entire curve. So anyway, we have example. Let's say our curve is 0L times 0. So the y-coordinate is always 0. X is only changing from 0 to L. So it's lying on x-axis right here, 0L, right? And then I want to apply this Cauchy-Crofton formula to this curve. So this is a line segment, but still line is a curve. So we just kind of think that this is a simplest example of a curve in two-dimensional plane. So what is the length? Of course, it's L. So we just need to check whether the double integration here on the right is L. And let's look at the n rho theta here. So let's see. Whenever we have this line, let's say our angle is this much, we have one intersection, right? We have one intersection from here, and then it can move up to here, right? So the line can be moved away from the 0 by this much. So how much is this? So let me draw a better picture here. So if my angle of direction is theta, the distance that I can move my line is from the origin until there is no intersection is, see, this theta is here and this is same as theta here. So this length, this length is L times sine theta, right? So L, so the rho can be 0 to L times sine theta here. So that's the maximum rho I can get until I get no intersection at all. And I only have one intersection, right? So because this is a line segment, two lines doesn't meet more than 2 points. So we have one always. So I just need to find the range of my theta and rho whenever n becomes 1. When it becomes 0, I don't need to take it as a domain. So just rho is changing from here to here. But now let's think about where the theta is changing. So there is intersection when theta is small, right? So here, and the rho is between here. And let's see, if I move far away more than pi over 2, then it's not intersecting this line segment anymore. So I only need to take from 0 to the pi over 2. So let's try to compute this. So this is kind of a Fubini theorem. So I just took the range of theta and rho when you have an n equals to 1. So this n rho theta is 1, 0. So it's 1 if it lies inside of this theta from 0 to pi over 2 and rho from 0 to L sine theta and 0 otherwise because there is no intersection. And I just used the Fubini theorem to make the double integration into iterated integral. And let's compute this. What is it? So we have 0 pi over 2 L sine theta d theta, and then this is equal to L times 1 over 2 minus cosine theta from 0 to pi. So let's see, why did I put 1 over 2? Why did I put 1 over 2 here? Right? I don't need this. So let's see here. Cosine theta is 2 pi over 2 cosine theta is cosine 0, right? So it's 0 here minus cosine 0 is 1. Cosine 0 is 1 and minus here, so it's L. Let's see. Oh, is it? Let me think of this again. So we have we can move away from here. So if I move the way here, I can still move away. So how about here? Oh, okay. So I can still move away when I pass the pi over 2, right? So I'm moving away from the 0 to the right, right? I can move away from the right. So so even when I pass the angle pi over 2, I can still move away to the right until I don't, and still like have an intersection between the line segment. So, but when I pass this pi, so when I pass the pi, then if I have the straight line going in the opposite direction, and then if I move away to the right, then I don't have an intersection anymore. So sorry, I have to change this pi over 2 to pi, and then recalculate this pi. So we have a pi. So then what happens? So we have cosine pi is minus 1, so minus minus plus L, and then we have 0, so it's 1 0. It's L plus L, 2L. So we had 1 over 2 in our formula, 1 over 2. So let's put the 1 over 2 back here, 1 over 2. So we have 1 over 2, which is L, which gives you the length of original line segment, which is L. So once you have this, it's quite automatic that this holds for every curve, because what we have done before is the length of a curve is just approximation of the sum of the lengths of line segments that connects the points on the curve. So these examples not only is true for the line segment lying on x-axis, it is true whenever we move our line segment around in xy plane. So it's actually about the integration by substitution, which didn't cover this video, but anyway, so each line segment satisfies this custom formula just by the same region in the example right there, and we take the small segment separately to calculate or approximate the small length of this curve, and then we combine them all together. So then we kind of approximate the entire curve using this right-hand side for each each line segment. And if you take the smaller and smaller subintervals, then we get exact length, right? So that's how we actually prove that this holds. So why is it so interesting? Well, of course, it's interesting by itself because it kind of connects two different concepts. So on the left-hand side, this length is about the single integral, right? So right here, so we kind of define that this length is computed by the single integration. And this Cauchy-Grafton formula said this, whatever the value we obtained by the single integration can be obtained by double integration, right? By clever choice of my function. And another interesting thing about this Cauchy-Grafton formula is that you can actually make a program that computes the length of the curve by just the image of the curve. Why? So what does that mean? So here, let's say let's suppose that you are given with the image of a curve. The curve can self-intersect whatever. So you have this kind of curve, and someone asks you what's the length of this curve. So assuming that we know the dimension of the length of the horizontal line and vertical line. So they ask, what is the length? Well, how do you answer this? So then, let's say this image is drawn in a paper. Maybe you can use your string to put it on the curve path and then kind of approximate, but that's not accurate. And also, what would you do if it's given by the graphical image? Are you going to find a parametric function? It's not easy. Or are you going to find points that connecting all those curves and approximate it? And how would you define, how would you separate this curve if there's a self-intersections? It's not easy, right? And how would you identify the point is on the curve? So there is more. So Cauchy-Crofton formula provides a very intuitive and direct way of computing the curve with a very nice accuracy. Just put your grid lines, lots of grid lines here on top of your graph, or assuming that your lines is vertical or horizontal lines are moving from the left to right or bottom to top with some kind of steps. Then you just count the number of intersections between those lines, imaginary lines, with your actual curve, and you just sum them up. So suppose that we just use these two type of lines. Then what is the angle between these two lines? They are pi over 4, right? So delta theta is pi over 4, because pi over 2, sorry, pi over 2. And let's say these lines, horizontal or vertical, are separated by a certain distance. So this is the distance between two consecutive lines. Then what you can say is that your L, the length of a curve, is approximated by 1/2 of this sum. So this double integration is basically the limit of sum. So if you take the limit out, then it's the approximation of the value. So just take out the limit and take the sum from 1 to n of this count times delta theta and delta rho. But then think about what delta and delta rho are. Delta theta is constant, pi over 2. And delta rho is also constant because we assume that this line is separated by the constant amount. So I can take this outside of the sum. So what happens is this is simply 1 over 2, let's say pi over 2 times delta theta, sum of all the number of intersections of these lines. So you can imagine the lines, these vertical and horizontal lines are right there, and just count all the number of intersections. Or you can move your lines, and whenever you move the line, you get the new line position, and then you just count the number of intersections, and then you do it for the horizontal ones and so on. So whatever you do, however you do, you just count the number of intersections with the lines and the curves. And you just take the number, and this is the integer, and you multiply these values, which is constant, and then divide by 2, you get the line. And the length of a curve, approximate value of length of a curve. So if you get the better estimate or better estimation, then you can decrease the distance between two lines, or you can not just using these two vertical and horizontal types of line, but you can also change the angle of the line is changing in a small amount. So this is kind of changing your angle in pi over 2 amount, but if you change by pi over 4 amount, you're kind of having a diagonal direction, horizontal and vertical direction, and then you just count again the number of intersection. But here you have a smaller delta theta, so even though you get a twice bigger than the number of count, it's gonna, you know, almost the same, but it gets actually better because you can get um, you can get you can get a kind of a better you can detect a subtleness of this curve by taking a different direction of lines to which might missed when you use these two vertical and horizontal types lines. So I'm going to show you how this can be implemented in the code and in the Pygame package. Okay, so in this separate second part of the video, I'm going to show you how to use Pygame package to make a game about finding the length of a curve using Cauchy-Crofton formula. So first of all, we need to install Pygame. Unfortunately, Pygame will pop up a new window, so you cannot use Colab to use Pygame. And in order to make a Pygame, you have to use your local computer, and you have to use some kind of IDE. You may use Visual Studio Code or other IDE like this one, Cursor. And you also need to install Pygame, or before you install Pygame, you have to install your virtual environment for Python and also install Pygame separately. So I did all that. So if you are new to this Python or Python environment, use ChatGPT or other external sources to get the solution for your own local machine, because it's always different for it's case by case. So I'm going to assume that everything is fixed, everything is set, then begin the coding. So I'm going to show you the basic workout of the Pygame. So it's going to start with the import Pygame, and there is a certain code that always has to be there in order to make this game work. So I'm going to set my screen to be the display set as 640 pixel wide, 480 pixel high, and I'm gonna put the play to be always true. And while play, I'm going to take an event from the get function, and event type is Pygame quit, then played false, and then Pygame display flip. It refreshes the Pygame window. So, and then when it's done, the Pygame quit. So I'm going to run this code and then show you what it looked like. So you see there is the window popped up, and there's nothing here because I didn't have anything going on, and there's a time it's running, so the code plug is still running when the game is running. And if I close this out, so sometimes it's frozen, so in this case you have to restart your kernel in order to abort this thing. So anyway, what I'm going to do is some kind of user interface. So I want the user to make mouse cursor click to make drawing of a curve. So here, I'm not going to delete anything. So here, so I'm going to add something. So if event type is Pygame mouse button down. Down means clicked. Then and also if Pygame mouse get pressed, so it takes it retrieves the x and y coordinates of where the mouse cursor is pressed, and I take so it takes the which mouse button is clicked, and I take the left mouse button, then I take the position of the mouse cursor, Pygame mouse get position, and then I'm going to make a small drawing, a small circle on that position here. Circle, screen, and with a white color here, with a size of 3. I don't want it too big here. And then, so this is when the mouse cursor is just pressed, and I'm going to have another code part which takes whether the mouse cursor is still pressed. So I'm gonna check if the mouse cursor is get pressed. So in the above here, it takes kind of an event here, and the next if this condition part is outside of this loop. So it's just checking whether the mouse cursor is pressed all the time when this infinite loop is running. So I'm going to take a new position here and then get the position, and which means that I'm taking a mouse cursor down, and then without pulling it up, I'm going to move my mouse cursor position. Then I'm taking that as the mouse is moved while it's pressed. So I'm going to draw the continuous line graph, but there's no continuous in the image. So I'm going to draw the line that connects the previous point to the new point. So the new point is new x and new y, and then I'm just use the line function to draw the line between the old one and the new one, like this. And I'm going to update my new x and y position. Okay, and then display flip to make the refreshing of my image. So I'm going to run this code again and show you how it works. So it seems similar, but now if I press this button, then you can see that the white dot appeared. And if I move my cursor while I'm pressed, it gives lots of white line drawn on this picture. Okay, so I can do this however I want, like this. So I hope it's okay. It's done. So let's see, restart again. Sorry, sometimes it's not working like this. So anyway, so we have user interaction with the mouse button. And now what I want is, I want to calculate the length of a curve when the mouse button is released. So whenever I finished drawing the curve, I want to compute the length of the line segment or curve here. Okay. Where is it? So okay, so the so in the outside, so if the event type, so I need to check the event type is whether mouse button is up, which means released. So if the event type is Pygame mouse button up, then it's released. Then I'm going to define a function called Crofton formula, Crofton length formula, with the screen as an input. So because already we have the game screen, some kind of a canvas to draw the curve. So I'm going to just take the entire image of the canvas of the game, and then just take that as an image of a curve to calculate its length. And then I'm going to convert the text of my length into a text kind of a text image here, a text value here. So the length value is the number, and I'm converting into with the 1 decimal point, and then render with 0, 0, 0 here. Okay, the font is here. Oh, by the way, so I need to import the font. So the font is Pygame font, system font, Arial. Okay, so Arial is fine. All right, so we have font, and we have text, and let's see. I'm going to fill the entire thing with the black color here, and then with 0, 480 here, and then update my screen with blit here with a text value. Okay, so the position is going to be 25. So 20 from the left, the width, yes, and 5 from the top. So it's going to be left top corner. I'm going to make appearance of this length value. All right, so I'm done with this code. All I need to do is define the Crofton formula. So let's define what the Crofton formula should be. So the Crofton formula, I'm going to define it here on the top. So here, the image is given by a pixel image. So each one pixel is a unit of length. So I need to set my step size to be the 10 pixel here and define the Crofton formula. Crofton formula with a screen input. And I'm going to output the float value here. So first of all, I'm going to take the variable number of intersection to be initialized at 0. And I'm going to take the image of a screen. There is a built-in function of Pygame that changes the screen image into pixel image, and pixel 3D is the function. And then get the size, height, and weight, width of the image of screen. Let's see. Although we know that it's 640 and 480, so I'm gonna use the get size function to get the height and weight. And then so I'm gonna take so I'm going to compute how many intersections are there for each line. So in order to do that, I'm going to take a 2x2 array of numbers called none here. So initially I initialize it to be 0 matrix with a width and height here. Oh, by the way, so I need to import the numpy here. So numpy as np here. And then so I'm going to initialize it like this. So whenever we have, let's see, not this one. So it's auto completed here. So if, so we have the range of height, which is the vertical index, to be in between of this 480, 620, 40, 640, and this j between 480. Then we continue here. Yeah. So, oh, by the way, so sorry. So it's not we don't need this. So I'm kind of changing the code from my book. So I'm just I'm confused with some of the parts. So what I'm going to do is I'm going to take the none as a 0 or 1 matrix, depending on whether the value of the whether the color of the pixel of the screen is black or white. So non ij is either 0 or 1. It's 1 if the image has a black color. 0 is 255. Otherwise, it's 0. So 255 means white, so it's 1, and otherwise it's 0. Right. So we have, let me erase this. Okay. So we have I in the range of 0 to the width with the step size. And we kind of now take the number of intersection added with some kind of the value, the result of intersection function. So intersections with non I here. Okay. So and also we do the same for j's parts to take a number of intersection, and then we return the number of intersection times the pi over 2 times the step size over 2. So we took the step size 10. I mean, if you want to take the unit of length with the coordinate with the according to the number of pixels, you can rescale it right here. But I'm kind of assuming that I'm here assuming 1 pixel is 1 unit of length. So I just used the original step here. Okay, so what is the intersection functions? Intersection computes intersections, number of intersection between the vertical or horizontal line. So here we kind of get the horizontal intersection by counting whether it's 0 or 1. So here I'm just counting how many times does black is turned into white. So if black is true at the beginning, for I in the range of this array given in the beginning, NP array and NumPy array here, it outputs the integer here. So if the non-I equals to 1 and is black, then now it's turned into white, right? So num intersection, no, sorry, so it's intersections has increased by 1, and we turn this into false because it's now white. Okay, so else if it's not, if the non-I is now black, now we make it into black again. Okay, so it only counts whenever the black becomes white, not white becomes black. Okay? And then we return the number of intersections here. So we're kind of done here. So here, S typo. So let's read again. So we have NumPy, and we used a conversion of screens into the NumPy array of image, and then we define the non-variable, which counts 1 if it's white and 0 if it's black, and then we take the number of intersections using intersection function to count how many times the black becomes white. And then finally, we give the cauchy-quantum formula. We use the cauchy-quantum formula to find the length by taking 1 pixel as a 1 unit of length. So let's run this code again. So every time I press the mouse button down, I'm going to draw the curve. And whenever I release the mouse button, I'm going to put the text. So I think I need to put the text into white color, right? So white color, not black. Sorry, white color 255. And yeah, so and also I'm going to erase all the curve that I drawn because I'm going to fill it with the black color. And then I'm going to show you the text value by the white color on top of that. So everything is going to be black except for the text image that I put on the top of the top left corner. Where is the typo here? So import NumPy. Oh, there's no module NumPy module. Okay, so let me go terminal. Right, so we have pip install NumPy. All right, so I think it's not working. All right, so now I'm drawing my curve, and I release my mouse button. Oh, it stopped. Okay, so it's okay, so no NumPy module. Okay, so that's the problem. Let's see, restart. Happens sometimes. So again, okay, so it's kind of working, but okay, so it's working, but I think I made a mistake on fill here. So oh yeah, I need to fill it with the black color, right? So black is 0 here, and let's run it again. Okay, so here is my curve. If I release my button, here's my value of the length here, and then if I repress it again, it's going to update my length. So you can change the code to leave your curve on the screen, even if when you release your mouse button. But I just made it into make this way so that the curve disappears whenever my mouse button is released. So in this case, you get the larger value. You can see it here. So it's very nice. I mean, I'm not saying that this game is nice, but this kind of Python package is nice, and also this implementation is not too hard, and you can see it's very interesting to see that you can easily compute by just counting the number of pixels or changing the color.